Okay, today we're going to kind of go back a little bit to what we did at the very end of last semester when we looked at we looked at approximating, I think it was the sine function that we did. But this whole unit that we're about to embark on is all about Taylor polynomials and about Taylor series. And we'll talk about the difference between a polynomial and a series in the next lesson. But basically, what we want to know or what we're trying to do is take a polynomial, okay, like x cubed, x squared, x to the fourth, x to the fifth, and approximate some other function with that polynomial. Okay, and so we're trying to get the two graphs and the two y values to line up. And the formula for an nth degree Taylor polynomial is, okay, so we're talking about the function f. N is the derivative that we're on, and we're centered at x equals c. This c value is our point of tangency. That's where they touch. Okay, so that's our point of tangency. So what we're going to do, and it follows a pattern, it's f of c times x minus over 0 factorial. So that would be the original function at the point of tangency times x minus c, x minus the center to the 0 power over 0 factorial. Then we move to f prime of c times x minus c to the first over 1 factorial. Then f double prime of c times x minus c squared over 2 factorial. And we go on and on until we get to the end, okay? This is called a Taylor polynomial, okay? Based on the name Taylor is the guy who wrote it. Now, if we want to be centered at x equals 0, again, that's our point of tangency. If we are centered at 0, it's the same formula, but it's called a Maclaurin polynomial. So when they say the word Maclaurin, you automatically know that it is centered at 0. And I'll show you how this works as we get into a problem. But for right now, you just got to be familiar with the formula. So it's f of c times x to the 0 over 0 factorial. And actually, this f of c would be f of 0 because c is 0. And then this one would be 0. So then it would be the first derivative at 0 times x to the first over 1 factorial, f double prime at 0 times x squared over 2 factorial, so on and so forth. Okay, so I'll show you how we're going to use this in a minute. Just some more vocabulary that we need to talk about. So the exact value is going to be the polynomial value plus some remainder. And that's what this guy says right here. So the exact value is the approximate value, that would be the value that the polynomial gives us, plus some difference between it, because they're not exactly the same, but they're really close. So the absolute error, okay, the absolute value of the remainder is going to be the polynomial value, the actual value minus the polynomial value. So basically, we're just moving that polynomial over to the other side like an equation. So when you see this right here, you have to know that that is called the absolute error. Okay, you've got to know that that stands for error, because a lot of times what they're going to say is just evaluate this and state what it means. So you've got to know that it's the error. Okay. All right, so let's actually try a problem and show you what's going on. Okay, so our function is natural log of x, and we are going to come up with a polynomial that will approximate natural log of x. So you know me, I like to be organized. Another thing that we need to know is that we are centered at x equals 1. So that goes down in this column right here. That means this guy is our point of tangency. This is where they will touch exactly. Okay, so we start with n equals 0, which means we want the original function, natural log of x. And if we plug 1 into the original function, natural log of 1 is 0. So then we go to 1. Now we want the derivative of this. So the derivative of natural log of x is 1 over x. If we plug 1 into the formula, we get 1 over 1, which is 1. Then we're going to go to 2. So now we want the derivative of 1 over x. which is negative 1 over x squared. If we plug 1 in, we get negative 1 over 1 squared, which is negative 1. And then if we want 3, we're going to take the derivative of this, which would be a positive 2 over x cubed, which would be a positive 2 over 1 cubed, which would be 2. Okay, so now we have all of our derivative values, and we know that these numbers here, 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 and here are going to go in place of that derivative spot right there. So when we go to write our linear polynomial, linear means we need to go to x to the first. So we're going to have our P1 of x is going to be our original, which would be 0. Well, let me do it. Okay, let me do this differently. Let's go 0 times x minus 1 to the 0 over 0 factorial. Plus, now we're going to have our next derivative value, which is 1, and we're raised to the first power, times x minus 1 to the first over 1 factorial. So that would be our linear polynomial. So remember our pattern, it's the derivative value at your center times x minus your center to the 0 power over n factorial. So 0 times x minus 1 to the 0 power over 0 factorial, then we move to 1. Okay, so now we're going to do quadratic, so we would call that P2 of x. That tells you the highest power of your exponent is going to be 2. That's why we designate it with a subscript. So we're going to continue, or we're going to repeat the first two terms. 0 times x minus 1 to the 0 over 0 factorial, plus 1 times x minus 1 to the first over 1 factorial. Now we're going to come up with our second derivative, which is negative 1. So we would say plus negative 1, and we would go x minus 1 squared over 2 factorial, and we would be done because we were only going to x squared. Now, for a cubic, we're going to go to x cubed, so we want P3 of x. So we're going to rewrite, and repeat the first three terms that we had. So 0 times x minus 1 to the 0 over 0 factorial, plus 1 times x minus 1 to the first over 1 factorial. I'm going to go ahead and move my negative out front. So minus 1 times x minus 1 squared over 2 factorial. Now we're going to pull in our third derivative value, which is 2. So we'll have a plus 2, and then we'll have x minus 1 to the third over 3 factorial. So it's a pattern that just repeats itself over and over. Now you will not have to write really a linear, a quadratic, and a cubic. You'll be writing one of those. Okay, so use P3 to approximate natural log of 1.5. All right, so let's see. Okay, I guess I'll do it on the home screen. Can y'all see my calculator? I think so. Okay, so this first term, because it's multiplied by 0, is just 0. So I'm going to ignore this first term. So then I have 1 times, okay, so 1.5 minus 1 would be 0.5. So it'll be 0.5 to the first power, which is 0.5, divided by 1 factorial, which is 1. So I'm going to keep that, minus, I'll come over on this side. So now I'm going to plug in this term. So it'll be 0.5 squared divided by 2, because 2 factorial is 2, plus, now I'm going to do in parentheses 2 times 0.5 to the third, close the parentheses, divided by 3 factorial, which is 6. So that gives me a value of 0.416 repeating. So we would say P3 of 1.5 is equal to 0.4166 repeating. So what does this represent? So this represents the approximation value. Okay, so now we're going to find f of 1.5. So remember our function was natural log of x, so we're going to do natural log of 1.5. And we're going to get 0.4054. So f of 1.5 is equal to 0.4054. And what does this represent? This is the actual value. That's a U. And so then it says find f of 1.5 minus p3 of 1.5. So that would be 0.4054 minus 0.4166, absolute value of that. Now, in your calculator, you do not want to truncate or cut off your decimals. So you want to go up and you want to pull both numbers exactly. So I get 0.0112, and this is called the absolute error. Okay. Now, what I want to do is I'm going to put into my graph the natural log of x, because that's my function, and then I'm going to put in my cubic polynomial. So that would be x minus 1 minus 1/2, so that would be 0.5 times x minus 1 quantity squared, plus 2 over 6 is 1/3, so I'm going to do x minus 1 quantity cubed divided by 3. And I'm going to do, now our point of tangency is at 1. Let's see, I don't think we need to go. Let's go negative 10 to 10 on the y. Okay, let's see if that looks good. Okay, so what we're talking about is you can see for some portion of the graph right here, they basically line up with each other, or they do what we call converging. They converge into a single spot. Now, 1 is that point of tangency, which is right here. So you can see if I trace to x equals 1, my y value is 0 on my natural log of x, and my y value is 0 on my polynomial. So we will always match at our point of tangency. Everything will be the same, okay? So this is kind of what we're looking at graphically and visually, is we're looking at the spot where a transcendental function or some complicated function, I guess you would say, lines up with a nice, pretty polynomial. Because, and this is what computer programs and calculators oftentimes use, a polynomial is much easier to compute than let's say a sine function or a natural log function. So a lot of the machines that we have, computers, calculators, etc., they work off of Taylor polynomials, believe it or not. So they'll do a 100-term Taylor polynomial to calculate the value of natural log of x, which, based on the number of decimals that are on the screen, it's exactly the value given that many decimals. So I just wanted you to see visually what we're doing. Okay, let's try another one. We have the square root of x is our function. So here's our function. We are writing a cubic polynomial approximation at x equals 16. So 16, remember, this is our point of tangency. Okay, so we're going to start with n equals 0. That would be f of x, which would be the square root of x, which when I plug in 16, I would get the square root of 16, which is 4. Okay, remember, we're plugging in our point of tangency value, not our n value. Now we're going to go to 1, which would be f prime of x, which is going to be, I'm going to write it with exponents, which would be 1/2 x to the negative 1/2. So that would be 1 over 2 square root of 16, which would be 1/8. Square root of 16 is 4. 4 times 2 is, yeah, it's 8. So now we're going to do 2, so that would be f double prime of x, bringing my negative 1/2 in front. That would be a negative 1/4 times x to the negative 3/2. So that would be a negative 1 over 4 times 16 to the 3/2. So that would be a negative 1 over, let's see, 16, that'd be 4. 4 cubed is 64. 64 times 4, I'm sure y'all could tell me, I think it's 256. Yeah, 256. All right, and then for our last one, 3, we have f triple prime of x. Bring my negative 3/2 in front, and we would have a positive 3/8, x to the negative 5/2. So that would be 3 over 8 times 16 to the 5/2. So that would be 8 times 4 to the 5th, which is 8192. So we have 3 over 8192. Now, you would not have to do this without a calculator. You could have a calculator for these numbers. All right, so the derivative values that we're interested in are 4, 1/8, negative 2 over 256, 3 over 8192, and remember they go into the derivative spot. So all it's asking us to do is write a cubic polynomial, so that would be P3 of x. So we're going to start with 4, so we have 4 times x minus 16 to the 0 power over 0 factorial. Remember, our point of tangency is 16. And then we have a plus, then we have a 1/8 times x minus 16 to the first power over 1 factorial. I don't even want you to worry about moving that 8 into the denominator. Leave that derivative up top. Then we have plus a negative 1 over 256 times x minus 16 squared over 2 factorial. And then finally, plus 3 over 8192 times x minus 16 cubed over 3 factorial. And that would be our Taylor polynomial. All right, it says use P3 to approximate the square root of 18. So our x value of our function, f of x is equal to square root of 18. F of x is equal to square root of x, and we want the square root of 18, then we're looking for f of 18. So we want to find P3 of 18. So I am going to put this polynomial into my y equals. So let me clear out what's there. I'm going to put the square root of x into y1, and then to y2, I'm going to put a 4 plus, because x minus 16 to the 0 and 0 factorial, that's all 1. So plus, I'm going to do x minus 16, let's see, I'll do a fraction. So I'm going to do 1/8 times x minus 16 to the first power over 1, and then plus alpha y equals enter. So negative 1 over 256 times x minus 16 squared over 2 plus, and I'm going to do my last fraction, 3 over 8192 times x minus 16 to the third over 6. Now, remember on this one, our point of tangency is at 16. So I'm going to adjust my window, and I think I'm going to go from 5 to 20. And let's go from -1 to 10. Let's try that. So there's our square root function. here comes our polynomial. So in a sense, they are, oops, can you see that? They are almost identical the entire way, okay? Now, if we trace to where we're at 16, our y value on our function is 4. That's our function equation up there. And our y value on our polynomial, oops, let me trace to 16. There we go. Our y value at 16 on our polynomial is 4 as well. Okay, but we wanted 18. So let me trace, go down to this one and type in 18, and we get 8689. Let me turn that into a decimal. Let me go to home screen and let me do alpha trace y2 of 16, and let me math decimal, not at 16, just kidding. Let's try that again at 18. There we go. 4.2426. Okay. Now let's see what the actual value is. So if I go to, or if I just do the square root of 18 is equal to 4.2426, where this is 267. So we're accurate to 4 decimal places. And then we're 0.00003 off. Okay. So then the absolute error would be the absolute value of f of 18 minus p3 of 18, which would be, I'm going to take this guy minus this guy, and I get 3.5094 times 10 to the negative 5th. Okay. All right, let's try another one. It's our last one. We have the function 1 over 1 plus x. So it's asking us to write a P2. So that means that we want a quadratic. So we need to go till n is equal to 2. So, what are we centered at? I think we're centered at 0. Sorry. Okay, so that's 0. So now we're going to go n is 0. So we're going to have f of x is equal to 1 over 1 plus x. If I plug in 0, I would get 1 over 1 plus 0, which is 1. For 1, I would get f prime of x, which would be negative 1 times 1 plus x to the negative 2, which would be negative 1 times 1 plus 0 to the negative 2, which would be negative 1. And for 2, I have f double prime of x, which would be 2 times 1 plus x to the negative 3, which would be 2 times 1 plus 0 to the negative 3, which would be 2. And then since we only want a quadratic, we don't need our next line. So then again, here are our derivative values here, 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 and they are going to fill in right there. All right, so P2 of x is going to be, we take our first one, 1 times x minus 0 to the 0 power over 0 factorial minus 1 times x minus 0 to the first over 1 factorial plus 2 times x minus 0 squared over 2 factorial. Okay. All right, so now it says use P2 to approximate 1 over 1 plus 1/2. So if this is our value that we're looking for, then this is our x value. So what we're really looking for is P2 of 1/2. And so that would be, if I do that one, it would be 1. Oops. It would be 1 minus, okay, so now my x is 1/2, so it'll be 0.5 plus, and this next one is 2, no, because 2 divided by 2 would be 0. So it would just be 0.5 squared, which is 0.75. All right, f of 1/2 would be that 1 over 1 plus 1/2. So that would be 1 divided by 1 plus 0.5, which is 0.66 repeating. And then what is the absolute error in our approximation? So that would be the absolute value of f of 1/2 minus P3 of 1/2, which would be 0.75 minus 0.666 repeating. So let's take this guy minus this guy, and it's 0.0833. Okay. Oops, let me put that on the screen so where you can see it. All right, so that's what we're looking at. We're trying to find, and that's what this whole unit is going to be about, trying to find a polynomial or a series to approximate a different function, another function, a more complicated function, a transcendental function, a trig function, a natural log function, a square root function, a sine function, okay, an inverse trig function. So all of those are complicated functions. And so what we're trying to do is we're trying to write a simple polynomial that will approximate those functions. And we're going to spend several days working on this before we move on to our next topic. All right, guys, that's it for today. If you need me, come see me. Bye.